start. So LTspice is around for quite some time now, and so Spice is a simulation program with integrated circuit emphasis. So this is engineers love to, I guess, name things, I guess, like this. But essentially, this is just a computer program that can simulate circuits. And so, not unique to Spice, but not unique to LTspice, but a lot of Spice software uses what's called netlisting and these types of netlist files. And basically, all it is, it's just a type of file that has these, I guess, abbreviations and numbers, and that can translate into a drawn out circuit. From there, it uses some sort of fancy multiplication matrices to find out values for circuit analysis. And this is really useful for engineers because, for one, we don't have to have physical components with us. We can just simulate everything online. And two, electrical components can be expensive. They cost, because they're physical, they cost money. They also take a lot of time. They don't take a lot of time. They take time to ship from the manufacturer to the consumer, and they also take a lot of equipment to operate. With Spice software, you can just instantly boot up a program, download the file, and just run it then and there. So that's really useful. In the lab, Spice is really useful because if you are building a circuit and you have no idea what it's doing, you can put that in Spice and see its characteristics. So that's a really useful feature for Spice. So this right here is, I don't know if it's really blurry to see, sorry about that. I can just do that real quick. So this right here is using Cadence, I think Allegro or Virtuosio, I forgot which one, but it's one of Cadence's tools. So if you really like circuit building, you can take either very large scale integration, or I think it's called Introduction to Op-Amp Design or Introduction to Semiconductors. But both programs uses Cadence tools. This is just the basic Miller op-amp. And so this is actually what's inside the little black boxes. So last semester I took Dr. Gui's Introduction to Op-Amp Design, and I built a little Miller op-amp, and yeah, I'll say fun. I wasn't like a nerd, but I enjoyed it. There's a few cheer shed, it was fun. Okay, so LTspice. LTspice is a free high-performance circuit simulation tool that allows users to design, analyze, and test circuit performance. So it's a mouthful. So it's developed by Analog Devices, which creates a lot of the little tiny black ICs. It runs on both Windows and Mac. And the best part, it's free and open source. So I mean, those are the best programs because you get to actually see what's happening underneath the hood. And if you want to make any modifications, you're free to do so. The creator of LTspice emphasized that while it is free, the purpose of the software is to basically advertise or just for the in-house chip designers over at Analog Devices to test their circuit simulations. But they have been grateful enough to share it to the general public, which is amazing. Okay, so now that basic intro, I'm going to open up LTspice. As you can see right now, I have this basic little inverting schematic. I'm going to open up a new page right now. I do that. File. New schematic. Okay. So I'm sorry, I don't have Windows. It might look a little different. If you're confused or lost, just let me know. I can try to help. But for Mac, I guess you're in luck. But anyways, when I open up this window, I'm greeted with this boring blank gray slate called Untitled. And so what I can do is, first thing first, LTspice is what's called a verb-noun program rather than a noun-verb program. And what that means is that when I have a program, let's say like Photoshop, but when I want to make an edit or a selection or anything for a particular image or layer, I select that layer, then I choose the edit. So if I want to, let's say, lasso tool or crop it, I'll select the layer, then hit crop. LTspice works the opposite way. What you do is if you want to make an edit or an action, you do the action command first, then you click on the component. So it's a little confusing, but it makes a lot of sense once you start actually building schematics online on the Spice program, and it's more intuitive. So that's called verb noun. So you do verb the action first, then you select what you want to do that action on, which is noun. Anyways, I'm going to go to this little blank slate right here. I'm going to right click, and I have a few options. Run it, halt it, view, edit, draft, draw, and a hierarchy. We're not going to really touch on hierarchy right now, but what you need to know is that if I have, I guess, a circuit within a circuit, like a sub-circuit, which is basically what these little black ICs are, I can condense that into a black box, and move up or down the service hierarchy. Okay, so I'm going to go to draft, and now I have a bunch of options here. I can do a wire component, net name, spice directive, text, data label, or bus tab. I'm going to go to a component right now. And when you download LTspice, I don't know if you have the option or automatically downloaded all of its example circuits. But you're given this little interface right here with all of these folders and a bunch of stuff. So you see, can everyone see this? I'm sorry. But I coach, I'll make sure. Pretty good eyesight here, which is great. So I can do my digital converters, comparators, whatever, all that stuff. I'm going to focus on op amps today. So I'm going to click on the op amp. And then down here is a list of a bunch of op amps. That's a lot of op amps. Okay. So what we're actually going to do, we're going to do something a little advanced. We are going to import a custom integrated chip into our program. So as you see in the top part, the top box of this GUI interface, we see the top directory, and this is where all of our files are located. Can everyone see that on their own device? No. Okay. Oh, you are. I'm gonna try to help y'all real quick. Yeah, I can.
So over that.
Yeah.
It just says.
It's show.
It's the same as
Show up there. Show all.
settles.
Yep, these are files. There you go. So on the little graphical interface, if you click down that drop down menu, it should have like all the in this directive it should have.
But when I press that, it's just a little like the file.
Oh, really?
Yeah. Just totally blank.
Yeah, it's completely blank.
Dang. They had to make it different. I don't know if I can do that.
Well, isn't that big of a difference if like you don't have access to the files?
Honestly, it's not for the purpose of an op amp, because an op amp is just black box that all you do, you put in something that amplifies it, so it's okay, we don't have to do that now. If for whatever reason we choose
Just
this
click op
files,
amps.
I'll learn how to add that on
Go to
the
all.
and I can show you all that,
Choose
so
op amp
it's not that bad, but for now, we'll use a basic op amp.
right here.
So I'm not entirely sure which op amp we're gonna use it on for labs, so I mean, I'll find that out soon enough. Anyways. I'm going to click on just a random op amp, I guess. Let's see what looks nice here. As you see on the left side, we have the symbol name, and then on the right side, we have a basic description. So let's just use the AD8091. Sure. So the single 10 millihertz op amp. Oh, it's actually kind of small. Sorry, I'm not gonna do that. I want to relatively high voltage. Let's see here. I was gonna use the LM sub for one test file, but see the LMs here. So this is post is pretty useful. That's the one that I imported. That's okay. We can use the LT 1001. Oh, not bad. So if everyone can search that in the box, everyone see that op amp. Called LT 1001. Okay. Hi. Haley.
Hi, how are you?
I don't want to do all things. Okay, so I'm gonna click that and add that on here. So I'm gonna zoom in. You can see me. All right, scroll up. And I can zoom in. So as you see, a few things happen right now. So I had the ability to place this component anywhere on the page. And once I placed it, I still had a little reflection of where I placed another one. I just pressed the escape button and I have exited the component placement verb, that's what you say. Okay, so on this PowerPoint, I have added a bunch of keyboard shortcuts that you can use. These are, if you want to be a pro user, you can use these. Not, you can also just use the click and select interface. As I mentioned, this is a verb now interface instead of a noun verb. But yeah, there's a lot of cool commands you can use here to make it look like a LTspice Pro. Yes. Okay, so what's really important, like computer scientists, we want to label our stuff. We want to make sure our schematics look nice and clean and pretty neat. We do not want, I guess, getty wiring. We want to make sure that everything's wired pretty neatly and everything's labeled neat. And there's a few reasons why we want to label stuff. Most importantly, when we are doing circuit analysis on the SPICE software, when we select which nodes we want to, I guess, look at, we want to make sure that those are labeled. We don't want like some default weird number node name that we can't really memorize well. So it's really important to label nodes. And there are different types of labels, I guess. There are input, output, and bidirectional. So input sounds pretty self-explanatory. You can just input a signal. Output is what comes out of the thing, I guess. And then bidirectional, if you want to do some more, I guess, computer engineering or whatnot, it can go both input and receive and output. The program actually does not, or your type of input does not affect the program. If I have a input or an output node, the program would just see that as just a basic node. So also, if you want common ground and it's published in, which is pretty nice, basically your VSS, it's at 0, just say common ground. There's also an additional one called com. This is just like a placeholder variable, not a placeholder, this is just another, I guess, ground, you can give it like ground 2. Sometimes it's really nice to have 2 different types of common grounds. So in this program, there's a built-in com port, which is pretty nice. I don't think we'll use it in the lab, but it's just good to put it out. So let's see. If I go here, we're just gonna do this real quick. I can go to draft, and then I can go to net name. And then from there, I'm put up the net name interface. Here's ground, which is also called global node 0, com, or my own custom name. So I can maybe call this PPD. And then I can make this nut, because PPD is your power, either an input or an output or bidirectional. I'm gonna press OK, and there we go. Good to go. I'm gonna place it up here just for now, and we'll get to this later. Now I'm gonna press escape, and now the PPD away. Okay. So another nice thing about node names is that we can treat node names like variables. So like in computer science, we have the variables x equals whatever, then we can reference x again. In SPICE circuits, I can have a node name, let's say VDD, and then instead of drawing a wire from the VDD from U1 all the way to like some power source, I can actually disconnect it virtually and then reinitiate it using VDD again. So I'll show what that means right now.
How do you do VPD?
Okay, so I'm gonna right click, and then I'm going to go to draft. And then from there, there's a thing called net name. Do you see net name?
Yeah.
Okay, cool. And then from there, I click on that, and I'm not gonna click GNG, ground, nor com. I'm gonna click the little text box, and then I can type in VDD. And because VDD is just a power port, it's neither an input nor an output. So I'm gonna leave the port type as none. And then once I press OK, select I'm brought up with this little thing, and then I can put it wherever I want. Okay, so I'm gonna wire. So right click again, and I'm going to draft, and first thing is a wire. And so now we're given this little crosshair thing. I'm gonna click the little part B, drag that down directly to plus sign, so rewire. Now, VDD should rotate automatically like that. The nice indicator that it is wired properly to the plus part. Just want to make sure, does everyone know why it's called VDD? Does anyone know why VDD is called VDD? No, okay. So usually in electrical engineering, the first subscript is, I guess, the data, you could say, and then, or the first script is the data, and then the subscript is where that data is being looked at or stored at. So V obviously means voltage. D is typically the drain. So we're talking about MOSFETs here. And so D means we're seeing the voltage from the drain to the drain, or drain to ground, I guess. But that's what we call VDD. Usually in op-amp design, you'll see all sorts of things. You'll see power, see VDD, you'll see DT equivalents. I'm just gonna stick with the so just for reference, like in lab, if there's any like thing that you're confused about, like subscripts or whatnot, just make sure to ask, because it's really important that, I guess we do understand what these mean. For me personally, like in circuit one, I was pretty stubborn, I didn't ask the subscripts for this, but then I was like, it was really bad for me personally, so, don't make that mistake, ask for subscripts, and most likely, if you don't know it, someone else doesn't know it, so yeah. So now that we have this little, interface right here, I'm going to actually right click again. I'm gonna create another VDD because I'm gonna connect that to a power source. So go to component. Not component, sorry. I'm gonna go to that name and then type in VDD again. Press enter. So that right here for now. We can move it later. And then I'm also going to right click here. And actually, let's see if I can pull this little shortcut again. I'm gonna press V on my keyboard to see if that brings the voltage source, and sure enough, it does. So right now, this is an undefined voltage source. V1 for now. Right here. And then I'm going to wire both VDD and the voltage source. I'm gonna go to draft wire. Boom. And just go here for now. And as you see, in order to fully place the wire, I clicked once and I saw the I can still like freely move around. I don't want that. I just want the wire from a little bit down the tail of the source. So I'm gonna press escape, and then I should have the remainder of the wire here. Then I'm gonna right click again. I'm gonna edit or sorry draft, net name, and move around. I can also press. I think I can press G for ground, but I can check out later. I'm also press ground right here. Escape. There we go. Yeah, G is for ground. Okay, so like I said before, you can think of the two VDDs as like this invisible wire that connects the two. What makes this really nice is that I don't have to have a long wire connecting two parts. So keep those two separate. That. Okay, cool. So we have our power. That's pretty neat. Let's have our negative power so we can bias this properly. So I'm going to basically do the same thing. It's kind of repetitive. Oh, does anyone have any questions or anyone lost so far? Good? Perfect. Okay. And if I'm going too slow, just like let me know. Go to that name. Now, if VDD is the bias or is the positive voltage, what would I call my negative voltage?
VSS.
VSS. Why SS?
Source to source.
Exactly. So I'm gonna do VSS. Let's enter here. And I'm gonna place one directly underneath the op amp, and I'm gonna place another one over here a little later. I'll press escape. Now I'm gonna go wire the two. Let's see here. It says that wire is F3. I'm gonna press F3. That up. Gonna wire negative rail to VSS. Nice. Okay. I'm a little lazy and I don't like doing things. I like if there's an easier way to do something, I will try to do it. So I'm going to select. Let's see if I remember how to select here. To go to edit, delete, duplicate. So if I went to edit duplicate, and I'm going to drag this whole thing, and boom, I have an exact duplicate of this. So I'm going to put it right next to here. Now I can select VDD. I'm going to right click. I'm going to go to draft, not sorry, draft. I'm going to edit, and then I can delete, which is F5. So, like I said before, this is verb noun. So instead of selecting the thing, I have to select the action first. So now I'm brought with the little scissors icon, I'm going to cut out VDD. And then I'm going to select the VSS. Let's see if I know how to select it. Move. So press edit move. I'm going to select this. And then now you have control over it. And now I'm going to put it up here. Nice. So we have our full power now, which is great. I think the next thing we should do is probably interface this op amp so it can actually do something. Right now it's just a little box that has power. Good for it, but doesn't do anything interesting. Okay, so now that we have that, let's make this an inverting op amp. Yeah, let's do an inverting op amp, that's pretty simple. Okay, so I'm gonna do the output right now. So again, I'm gonna do FN3 for wire. I'm gonna actually escape. Sorry, I usually do this with the mouse. I forgot my mouse right now, so I have to bear with me with my trackpad. So I'm gonna wire up the output like this temporarily. And now I'm going to, I'm actually move the SS and DVD pretty close to the input terminal for the op amp. I'm gonna edit, I'm gonna move. I wonder if I can drag it. I can drag it. So I dragged it, I selected both powers. I'm gonna move it a little bit to the left, you can move it more if I need to later. Okay. Now we have room to freely draft the inputs. So in my inverting amplifier schematic, what do I draw for the positive terminal of the op amp? For an inverting amplifier. Ground, exactly. So I'm gonna just put wire here, maybe I'll make it go down 90 degrees. Done with that, press escape. I'm gonna press G for ground. Like that. Boom, we got a ground terminal. Pretty nice. Okay. Now let's do our negative terminal. Does anyone need help with anything or have any questions? Sure. I'm gonna go up to the negative terminal. Again, I'm gonna do FN3 for wiring. And I'm gonna just do a little port right here, press escape. But now I'm gonna add a resistor, add 2 resistors, of course. So I'm gonna press R, and R brings up a little resistor graphic. And now if I do Control R, it's Control R for both Mac and Windows. I can rotate it, so it would make sense if I want my negative feedback resistor in a vertical configuration. So I'm gonna rotate it to horizontal, put that here, and I'll put my second one right here. Now, the really nice thing about Spice software, like LTspice, is that when I place multiple components, it automatically increments its variable name. So as you can see, I don't have to even configure it, but it already set the names of resistor R1 and R2, which we're pretty used to see. I'm gonna go ahead and create again. I'm gonna go wire now. So one wire here, one wire. Let's just put it right here. Press escape, and now let's do our negative feedback. So I'm gonna go in between R2 and B1. Go up here. Click. Boom. As you can see, whenever there is a node, it automatically creates a little node for us. So that's a nice indicator showing that we have created a node. So I'm gonna go click on the N terminal R1 here, all the way down. That should create a node. Boom, look at that. Pretty nice. Looks like it's inverting amp now. Now we need to have our actual signal source. We have our powers, but because there's nothing in it, there's gonna be nothing going out. I'm gonna drag once again the voltage sources. So I'm gonna edit, move a little bit right there. Okay, so as you can see in the interface right now, if I go to edit, you can see both move and drag. Move is you completely just like have a wire, you can move it without altering it. Drag, on the other hand, will take that wire and it will. Oh, well, it should stretch it, but let's see. Maybe I'm wrong. Yeah, actually, I don't know the difference between move and drag is. Okay. Usually in Spice software, I'm used to Cadence, I'm sorry about that. In Spice software, you can stretch something. Basically, everything else will be anchored in place, but that wire or component will be, I guess, quote unquote stretching. That's, I guess, we're all in right now. Okay, I'm gonna go draft. Actually, no, I'm gonna copy and paste BDB again for my signal source because I'm lazy like that. So I'm gonna edit, duplicate. I'm gonna go drag BDB. And it does not do everything. Edit, duplicate, all the way. Bam, there we go. Nice. Okay, I'm gonna place this. I'll place this here for now. Then I'll move everything a little bit to the left, so I can have some room for my variable name. So edit and move, drag all of this a little bit to the left. Nice. There we go. Okay. I think now what I will do is I will label my nodes. Right now, if I were to run it, obviously the input would be right here, and the output would be obviously right there. And then that will be the program will give me some random number names. That doesn't mean anything to be honest, so I would actually have some names on there, so. Going back in the menu interface, I'm gonna go to draft, and I'm gonna go to net name. So what should I call my input? Just VM, I guess. And if you want to be a little fancy, you can call it an input. And so it brings up this little flag right here. And this flag is common across the majority of Spice software. There hasn't been a Spice software I use that because it has something like this. So when you are reading schematics, you see a little flag, the arrows go like that, you know, as the designer or the engineer, that means the input.
How'd you get the flag again?
Okay, so if I go to draft net name and I type in, right below that is port type or somewhere on Windows. Hopefully Windows shows that. Okay, cool. So port type right now is selected to none. And when I click on that, I do input, output, and bidirectional. So we do input. So input right there, and I'm gonna click that right here in the beginning. So we have our input, which is en. Now I'm gonna do the exact same thing, but for v out. So draft, net name, v out. Port type is obviously an output, since it's going out of amp. And the only difference between the input and the output flag is that they both look the same, except that you put in the little triangle parts of the input to the wire input, specifying that it is input, and the output is the tail end, I guess, going in that. And then just to show y'all bidirectional. Bidirectional looks like both little triangles. But I'm pretty sure we won't use that. So I'm going to delete this. Go to draft, sorry, edit, delete, and then get that out of there. Okay, cool. So now we have some nice labels. Oh, one thing real quick, as you can notice, because I duplicated BDD is there twice. So I'm going to go right click on one of the DVDs, it really doesn't matter, and I'm going to call this VN. That way it can match both VNs. Cool, so now that we have our components placed, let's go actually start assigning some values. Because right now these are generic resistors, these are generic power sources, we actually don't have values yet.
Would it be the same if instead of using the labels, we just plug the VN battery straight in?
Yep, it's exactly the same thing. So one reason why you want to use the net names, or sorry, the labels, is because we don't want to wire it. So when we have more complicated schematics, we have a bunch of components that we need to wire, and to make things a lot easier, rather than like putting our finger to the schematic and tracing it back to the source, we just have variable names that we can put the reference back to. Okay, so on to VSS VB, VB, I'll right click VB, and it brings up the DC value that I input. So I haven't used not that familiar with LT10014, so I'm gonna go to Safari, and I'm gonna bring up my good old trusty data sheet. So LT101 data sheet, and on devices, that's the wrong product. And I brought up with this nice, it's a pretty nice layout like that. Okay, simple application, we got it. Nice two. Okay, so I'm gonna scroll down. I told someone to do this. Make sure you're seeing the recommended ratings, not the absolute ratings. I don't want to like push it to the absolute limits, versus blowing up. But anyways, we go to electrical characteristics, input range, see typical 14 volts. Okay, sounds good. DC value, all right. Let's do 7 volts. We'll do 7 volts. You'll see why later. So as you can see, it instantly changed to 7. That I changed it to 7 volts. And then on VSS, you can right click that, and I'm going to do minus 7 volts, so it's properly biased. Okay, so now I want to change my VN. So this is going to be a little different because we don't want a DC voltage input. That'll be kind of boring. These op amps work really well when we have AC signals. So I'm gonna right click this. And I'm gonna type in, let's do this first, I'm gonna type in all caps sign and press enter. So now it brings up another interface when I right click again. This is a more complex interface for AC signals. Does everyone see this interface? Or
How did you do that?
Okay.
Would you click on?
Okay, so what I did is on the webinar, I right clicked on the power. Actually, I can show you on here. So like, imagine BBGs again.
Oh, okay, I see.
Okay, cool. So I'm gonna right click on here again. Now it brings me up to the AC building interface for power. Yeah.
You went to, how do you get there?
Oh, I got you. Okay. So on, let's just say, imagine BBGs again. I'm just gonna right click on that, and for the DC value, I'm gonna type in sign in all caps. And then there I press enter, and it should say sign, just like this.
Yeah,
So once you see that, right click again, and it brings more bigger interface. It may be a little intuitive, but it's a pretty good, I'd argue it's a good workflow. But can you see this interface?
yeah, I see.
Okay, cool. Okay, so now I'm brought into the AC signal interface. If I click on style, I'm given a bunch of options, so I can do sine, exponential, I don't know, and then DC. Okay, so I'm gonna focus on sine right now. And then in the parentheses, it gives me a bunch of different variables. If you are a pro coder, you can directly just type that into the DC text box, but I like interfaces because they make more sense to me. So I'm gonna use that set. So the DC offset, we're gonna have 0 for now. Amplitude, let's just say 1 volt. Frequency, let's just say 10K. And that's all the information we really need right now. So once we have that, we press OK. And then, as you can see, it fills it in magically for us. We have sign and parentheses with a variable. So as you see, just offset 0, your voltage is 1 volt, and then your frequency is 8. Okay, so next I'm going to assign R1 and R2. I'm actually going to rename these. I'm going to call this little R1, R1, I'll call it top 1, R2, just because we're a little more used to that. Yes, Andy.
So sort of a stupid question, when you put in the voltages, I noticed you can put in just numbers like you did, or you can put in like V. Does it matter?
What do you mean?
Well, like error if you put in 7V versus 7 for the
Let's see,
voltage.
I'm gonna test that out later. Yeah, we'll see. That's interesting. It might. My guess is that it won't throw an error because this program can detect prefixes like K, M, and then it uses P and R to represent the component type. But we can try that later. Anyways, so what I just did is in the top of R2, I right click that and I have the opportunity or the option to change the name. So I just changed it to R2. You can change whatever you want. Say for you as the designer to do this better. Okay, so for R2, I'm gonna change, I click on the active resistor and I'm gonna change it to 5K. 5,000. Okay, and then R1, I'm gonna change this to 1K. Okay, so right off the bat, does anyone know the gain of this amplifier?
5.
Was that?
-5.
Yeah. And typically when we say amplitude, as in like its absolute values, like its absolute gain. So I'll just say this has a gain of 5, but you're right. So you find out the gain of inverting amplified, inverting configured amplified, or sorry, inverting op-amp configuration is just negative R2 over R1. Pretty simple. The designer, I just need to choose the ratios of 2 resistors to get a nice gain. And that's a really nice feature about a lot of op amps is that we're able to get nice ratios that we have control over when we're designing stuff. Okay, I think we're good on this now. If you wanted me to agree, I'm not gonna worry about that too much. So what I'm going to do now, I'm going to press the little running man icon right here. And if all works well. Oh, it says no analysis comment found. That's not good. So it actually failed, and it's because while we do have the schematic, we didn't tell the program what we want to do. So in schematic analysis and circuit analysis, we can do a bunch of types of circuit stuff. So we can do DC analysis, AC analysis, transient analysis. There's a bunch of stuff we can do. So let me see. So on here, I think I wrote, yeah, here we go. Here are all the types of, we call these dot commands that we can perform. And so the dot is basically like, it indicates the program that this is a command that we want to do for this particular schematic. So a lot of things, I want to basically have a virtual oscilloscope that makes sense in our program. Oscilloscope is a form of transient analysis. So what I'm going to do on this interface is I'm going to right click and I'm going to go to edit, not edit, draft, and then spice directive. And it brings up this little text box. I think of it like a little terminal command. So I'm going to type in .tran for transient analysis. And then I'm going to do the time I want to perform that analysis. Let's do 6 edges now. Then when I press enter, we need OK or a new line. I'll just press OK. Now I brought up like a little text box here. I can place that wherever I want, doesn't really matter. So whenever there's a dot, think of it as a command. When there's not a dot in front of it, there's no command. It's just a label for us to see. Okay, so now that we have that, I'm going to run it again. And it brings up this black box. Does this black box show up in everyone's screen? No. Okay. Are you getting any errors?
Spice output log.
Output log.
I heard the wrong thing. Because we don't have
You
learning
can't
yet,
text
so
it.
I did
But no.
This one.
Oh, yeah.
Yeah.
That must.
For everyone else, does it show little black box? Cool.
The chat black box.
Wait,
where?
Right there?
When we click run?
We just have a green triangle.
Yeah, you click run and then the little black box should show up. Cool.
We did.
Okay. So this, and then it brings up this little plot. So the nice thing is that as you see, I performed 0.6 M, so that's 600 microseconds. That's complete extend from 0 to 600 microseconds. Right now I have a black box, but that's actually what we want. So now this is our little, I guess, interface we use to see what our circuit is actually doing. And so when I have, it's really useful to have both windows open. There's a few ways you can see the circuit. I'm going to show you what I think is the easiest way, and that's all you do is you hover over the schematic, and you see I'll hover over VN, and you see a little probe. And I'm going to click on that. Boom. We got a nice signal showed up. So as you see, our x-axis is the time, y-axis is the amplitude. So as specified, we have a 1 volt peak. Got a 1 volt peak. And I'm going to click the out as well. And there we go. We have our 1 volt peak begin, and we have 5 negative 5. And notice because this is a inverting amplifier, we have that phase shift. So that's that's the characteristic of the inverting amplifier. So was everyone able to have this output? Yep.
Should go over that one more
I
time.
got you. Okay, so I'm going to initiate it. Okay, so when I touch Running Man for Mac or the green button on Windows, I'm brought up with this black box. There's nothing on it. If you want to see the signals, I'm going to click on the black box to make sure this window is selected, and then I'm going to hover over the other box of the schematic. And I can, if I hover over any component, I'm brought this little probe interface cursor. And so that means I can click anywhere I want. So I'm just going to click on the ladder at the end. And from there, a little graph shows up what the end looks like. You see that?
Mm.
Perfect. Okay. I'm going to now hover over V out. And I'm gonna click that as well. And then V out shows as well.
Thank you.
Were you able to get that one here?
Yes.
Okay, perfect. Cool. Another tool that you can do is if you wanna see the, oh yeah.
How do you clear it entirely?
Okay, so to clear it, pretty sure, I mean, what I just did is I just press run, or I exit out and press run, and that like resets the whole thing. I'm sure there's a more official way of doing it. Right now. I used to, no, I exited out, I guess I wasn't able to do it now, but anyways, yeah, I just exit out the window and I just press run again. But, voltage is not the only thing we see. If we go hover over a component, let's see like a resistor, we're given a weird icon. This is a current, ammeter, there you go. So a little circle with the arrow running through it, that actually click on that. That can show us the current running through a component. So, like I said, if you are in lab and you are wanting to find out values, if you don't want to do the analytical method, you can just whip it up on Spice and see what values show and give you a good starting point or a nice guessing check. Yep.
You do current.
Okay, so when I'm hovering over the wires, I'm showing this little pro icon. But if I hover over a component, like this resistor, that little icon changes. So it's the little circle with the arrow going through it. Right now this graph looks really messy, so please bear with me, but as you can see on the top, this is where labeling comes into play. The green one represents V in, blue is V out, and then the red is I, which is R1. So this is current showing R1. And as you see in the left hand side, we see the voltage shown, right hand side, we see the current. And then obviously the x axis, we see the time passed. Okay, this is a lot for me, so I'm gonna exit out, run the man again, a little bit. I'm gonna show the in and the out. Okay. If I click on the little graph, I can drag little blocks and that will zoom in. Pretty nice. I can zoom in even more. This doesn't really show me anything, but I can just show you how much you can zoom in. Pretty cool. If I click on the little magnifying with the X, that resets my view. Okay, next I'm going to see, there's another way that you can, I guess, graph stuff, and that's adding traces. This is, if you're more of a computer science person, you can type in the variable names and what you want to see. Right now, it's giving all your variables for me, so let's say I want to, for whatever reason, graph BD, sure. There you go, got a nice straight line, it's pretty boring. Okay, I can also,
How did you do that?
okay, so there's an icon, I don't know if you see it up here. It looks like a little line inserting into a graph, and it's called add trace. And so if I click on that, I think it might look a little different on LinkedIn, but it should be called add trace. And when you click on that, it brings in this extract spot. And from there, I can just type in the variable name and it can show that is. So I can type in, for instance, V, parentheses, the voltage at Vn, press enter, and it shows that. So that's an alternative to going to the other window and clicking on a wire or component. Yeah.
So whenever I hover over the op amp, I just get like a hole, but there's like no current going through it. What's that mean?
You're sorry, you're what?
Whenever you like hover over the op amp,
Yeah.
like the plus or minus, it's like the same symbol for the resistor, but there's no arrow going through it.
You hover over the op amp. Are you saying, oh, the
Like
hole,
the
you see
plus
that?
or the minus.
Okay, so what that is that is a current indicator. So this little graph, I'm pretty sure is the tool you use to show the current going through something. That's why it looks like that. If you want to see the voltage, I would hover over the wire. It changes to a probe.
Well, what I'm saying is it's different from when you do it on the resistor.
I see.
Yeah. Like resistor, it has the.
Yeah, so when you
arrow through it,
whenever
but
you
here
go
it's just the
over
normal
whoa.
hole. And then you get like some weird stuff.
Your stuff is pretty weird right now, but so whenever you have that, whenever you hover over a component, that's gonna show its current. If you want to show the voltage, you probe it. But as y'all know, if you want to measure the voltage of something, it's not just at one point, it's usually at 2 points. So let's say I wanted to see the voltage across R1. What I would do graphically is that I'm gonna click on the graph, actually I'm gonna pull up a new graph real quick. Okay, I'm gonna hover over a little after VN, I'm gonna click and hold that. And then I'm going to, whoops, click and hold that. And then as you can see, a probe stuck, and I control another probe. And so now I can bring it, let's say, the other end of R1, and then now that probe will change black, I'm gonna release, and it shows the voltage difference between the two. So if you ever want to measure the voltage differences, you click and you hold, drag to the other part, release. So again, do R1, click and hold, just go all the way back to R2, release, you see the voltage difference. That's pretty cool. Okay, so if you are doing SPICE, some of the labs you'll be required to simulate this in SPICE, to show your work or show your output, I would just take a screenshot, to be honest. You can be really formal and save it, or you'll save it as a PLT file, and can't really open that easily. You'd have to have some external program. So on Mac, I have just the simple screenshots command. You can go insert setup, do whatever you want. But make sure that your axes, I can understand what your X and Y's are, as well as your names up here. If you have a random name, here, let's do that real quick. I'm going to, instead, I'm going to exit out of this. I'm going to delete the out, and let's see what that does. So, with the edit, delete. I'm gonna run this here and click on this. Okay, so the V is the voltage, but then it says N002. I don't know what N002 is. I can't even tell when I look at the schematic, so I'm gonna assume that's like some foreign signal coming from space or whatever. So I got that. I'm gonna undo. Edit, undo. That's okay, so Sam brought up a pretty interesting point. What if we have for I guess a voltage or anything we have V. So for VDD, I'm just gonna experiment this instead of 7, I'll do 7V. I'm guessing this won't change anything. Yeah, it doesn't change anything, everything works the same. So the program recognizes if you have V. If I want, I could do 7 kilovolts. So that looks like this is weird wonky signal. Now this is one of the limitations of see in. There's V out. This is one of the limitations of this program is that I'm pretty sure if you put in 7,000 volts into this precision op amp, it will probably explode or burn. So please don't put 7,000 volts in your op amps in lab. Appreciate that. Okay, I'm gonna change this. Just a second. Okay, let's go try another thing. So I'm gonna edit V in. Actually, I'm not gonna edit V in. I'm gonna edit R2 to be 10. Actually, let's make it to 20K. Now, do you think that the peak to peak output voltage will be 20 volts? Why not?
It's gonna clip.
So clip, why is it gonna clip?
Because we only have the voltages set at 7 minus.
Exactly, so we have a peak to peak voltage of 14 volts. So when we put a gain of 20, it's gonna theoretically clip. I see it there theoretically because this is a mathematical software. It doesn't do actual physical stuff. That would be analog. So the in, looks pretty normal, the out. Look at that. So we see 6 and -6. And then we also see this weird phase shift. There's not perfectly opposing each other. And we see some clipping on it. So you're right. So like I said, in lab, if there are questions that you're uncertain of, throw it in SPICE, mess around with it, have fun with it. So we do also other interesting stuff. So one more thing I'll do is I'll set this back to 5. For our sinusoid input, let's go make the amplitude, actually let's make the frequency. I'm gonna go check this data sheet. And I'm gonna see. Let's see our voltage.
Are these simulations live? Like if we change the values after we ran it, do we have to run it again to see those changes reflected?
Whenever you run it, you would have to rerun it. Or sorry, whenever you change values, you have to rerun it.
So is there like a live version or do we just have to rerun it every time?
You'd have to rerun it every time. I will say, if you want to have an intuition for how circuits behave, I guess, one program that I started off with is called Falstad, free online website. Here, I'll just right now, Falstad right here. And the website's literally this guy named from Paul Falstad. And so you have this HTML website, and you click on Circuit Simulator, and it brought to this little interface. So one thing that's nice about this is that it can display or simulate current flow. So you can have you can gain an intuition of what that looks like. I would recommend using this for like circuit analysis. I prefer using SPICE software because you get more detailed information from that. But Falstad is a pretty decent option if you want to have, I guess, some intuition or you want to make quick calculations or not. But right now, I'm going to focus on LTspice. I guess the last thing I'll do is I'll change the frequency to 10 megahertz. Let's go run that, see what that looks like. Looks like nothing. So probe it. Boom, boom. We have some weird stuff going on right here. Oh, that's actually kind of weird. What's going on? So it seems like this op-amp cannot take this high input, so let me just runs out. It looks like change this to 100K. See, performs better. There we go. Okay. So here's 100K. Obviously, we would not want to do 600 microseconds at 100K. If you get this green graph, zoom out. We got some weird looking stuff here. And then this is where zooming in can play. You can zoom in, zoom more. XCI enhance. Doesn't do much of a good job. We just like change some settings. But I encourage y'all to mess around with this in lab if y'all want. Let's see, 828. I may have enough time to go over. This result. If anyone have any questions about my software. So in the first lab, I don't know if y'all checked, y'all will be making a few basic op-amps. I will upload this particular file to the Canvas lab page. And when y'all do make y'all's lab reports, it's not going to be in the lab instructions, but I do want y'all to simulate every single schematic. I think there's only 3 schematics on there. Let me go double check. I'm having this weird glitch where SMU websites don't load when I found Safari specifically. This was yesterday. Oh, there we go. Cool. I'll get to see what class is. Okay, so I'm going to go to files. Go to the first lab. Let's see. Pretty sure it's 3 op-amps. Inverting, non-inverting, 1 1. So, there's your inverting, it's the one we did. There's non-inverting, and cascade. Okay. And then cascade, that's when your voltage difference probing can come into play because you can see the voltage difference between the input in the first gain stage, and the first gain stage, the second gain stage, and then all together. So that's pretty cool. Okay. Any questions? Anything? Oh, cool. I think maybe what I can do for the remainder of the time is I guess I can go configure the inverting op-amp on breadboard. Just like a quick walkthrough. Should I do that now, or should I do that in the first lab section next week? Which would you all prefer? Time now. So time now. Quickly go over it. Okay, so that. Let's see if I can. This is gonna be really interesting. I have an idea. Okay. So I'm assuming that everyone here has used the oscilloscope in Circus 1. So I don't have to explain what it does. I kind of took this from lab. I'm not sure if I'm supposed to do that or not, but just for demonstrative purposes, I brought it for y'all. That does not reach. I'm gonna plug that here instead. And so in lab, you'll have, I think, the exact same model, digital oscilloscope, which is pretty nice. This thing does the job pretty well, and that PowerPoint has no supply power, so that's a scam.
So she wanted to figure
That's also a scam. And that does not reach. I should have brought extension cord. Oh, it's not. Okay, that's why. Oh, okay. Okay, also, Dr. McFarland has bought these little $50 spectrum analyzer boxes. I messed around with these the other day, they're pretty cool. Has anyone messed with the spectrum analyzer before? No. So all it is a little black box that can display signals or the amplitude of a range of signals. And so this one is, I think, intended for radio hobbyists. So it just plays up to, I can say, 35 megahertz. I'm not exactly sure. 350 megahertz. There we go. On the low end, and then up to 960 megahertz on a high end. So pretty high frequencies. We're not going to deal with this high frequency. We're probably dealing with like lower frequencies. But it would be pretty cool if I don't know if we're gonna have more of this in the lab, but we can definitely mess around with them. I like equipment a lot. I like things that display stuff, and so I kind of nerd out with these types of things. So y'all have to bear with me during lab times. Another thing that y'all would probably know is that when you're building breadboard circuits, anything that's physical, that has physical properties involved, anything and probably everything will go wrong. And so I've been building breadboards for some time now, and still I have random problems that can be really frustrating and annoying. And I'm sure that y'all experience the same things in circuits one. And probably will experience the same things in circuits two. But the good thing is that we're all in this together, so we all could stay strong, I guess. Okay, I want to see if I can. What did I do? I disconnected it. That's unfortunate. Uh-oh. Let's see. Okay, actually, this is really dedication. Now it's not in that space. Right, there we go. Perfect. Okay. Let's see what I can do. Ooh, must be from doing this. Yeah, it's just this today. Yeah, it does. I'm gonna slowly move my laptop over here. Do y'all know that like we have like a bunch of money spent on technology. This is what we get. Okay, there we go. So now I'm going to go to. I wonder if I can change my video. Perfect. Okay. I don't want the background though, so I'm going to change the background real quick. Video. Does anyone know how to like unblur it? Right.
I think it's under background.
Yeah. Partial background stuff. Dang, I feel like it's
Check video filters.
Yeah, I think I'm good. Okay, I do this entirely. Okay, this is a really janky.
Also, I just want to mention,
Yes.
oh, never mind.
Okay.
I was gonna say you were muted, but you're connected on your laptop
And then I'm pretty sure that Junkin is recording my voice.
Yeah.
So.
Doesn't matter.
Okay, so y'all can see the oscilloscope. Perfect. Okay. I have this little breadboard I took apart. I'm going to quickly put it together. I don't know if y'all can see this. So I'm sorry for a really bad camera angle. I'm pretty sure you can view the a desk view. Oh, desk. FaceTime, HDUS. No, I need it through my phone and you put it like through a little thing there. I don't have that. I'm not too deep to Apple's ecosystem. Okay. I'm gonna go put my little, so I'm using an LM741 right now. I grabbed this from my lab desk, and to be honest, I don't know if this works or not. So if it doesn't work, I apologize for wasting your time, but figure it out. So I'm gonna place that right here. And for integrated chips, these types of chips that have the little pins are called DIP chips, DIP chips. We usually use those for breadboardings. And then whenever we have PCB, for printed circuit boards, we use what's called surface mounted device or SMDs. I used LM741s in Circuit 1 lab quite some time, so I'm used to the pinout. I do not have to reference the data sheet for that. And usually you reference the data sheet for the pinouts. So I have what's a 5K resistor for R2 and a 1K resistor for R1. I'm gonna connect the power to the power rails. And I'm not gonna bias it because I don't, I do, but that's okay. I'll just keep it to B++. B minus, I'm gonna put it to ground. And I'm sorry for my wiring, this is really messy. And also, I don't know if y'all can see, but when I build my breadboards, I like to have it in a horizontal configuration. Just because the power rails are on the top and minus, and like the schematics, I like to put my power at the top and my B minus I have the ground and bottom. So I have my ground bottom. Cool, okay, I can figure that pretty quickly. I'm gonna now put in my power and my signal source. And I get the purpose of me doing this right now is just to compare the simulation to the actual physical model. And then again, it may not work because it's maybe a burnt op amp that I forgot to throw away. Also in lab, if you ever burn a component or a component does not work and you confirm that it does not work, just throw it away, please. Don't put it back into the bin for someone else to use and discover that it does not work. That'd be pretty devastating. So I have these janky wires right now I use to connect my power. And then while I'm doing this, I'm just curious, is anyone involved in like, what are you all involved in besides engineering?
Nothing.
What do you mean?
Like
This is a room of engineers.
I know y'all are doing some fun stuff.
Doing another major.
What?
I'm in a sorority.
Engineers without borders.
Engineers without borders.
Double major.
There you go, dance.
Alpha Chi.
Yes, sir.
There you go. There's fun stuff
Make
that
us
y'all
feel
do.
like.
And I think
Oh,
like,
yeah, that's okay.
I don't know if y'all did this in circuit
Like, come
one,
find
but
me.
like, my group definitely, like, there was some bonding done in circuit one lab. And so
Really?
it's definitely important to know your fellow peer engineers. So at the end of the day, when we all go to industry, we're probably gonna, there is a high chance that we'll work with each other. So it's important to know what we like, and our hobbies and all that.
We
I'm not
definitely
working
did
as
that
well
last
in industry,
semester.
that's for sure.
Really?
We
Wait,
bonded through
I wasn't bonding with my lab partner, but yeah. the rest of
I was
us.
the only person in my lab section.
Oh, yeah.
Drop circuit.
Okay, cool. So I have this power.
Like he's
Gonna-
switching
like-
tracks.
Yeah. He's like,
You still need circuits too, no matter what.
Okay, I got my
He's not on the
BNC to Allier cables.
he's like the.
Okay, so real quick.
Something like.
I couldn't keep doing computer shit.
I'm done with my
Let's do one real quick.
With what?
School?
Oh, fuck.
My wires.
You know 3330 that I told you I like was going to do? I had said sign up for the 5,000 level computational neuroscience. Oh my god, I saw the book for that. It looks awful.
And actually, dude, isn't it all math hard? Isn't it all math levels?
Take it next year.
That's true.
I'll be in the next year.
But I just those classes.
Adaptive algorithms.
Yesterday was the last day to add drop classes, but yesterday was also the first day in celebration. So I didn't know if I was gonna be able to myself or if I was gonna have time to do. So I was like, I don't know. So now it's too late to add drop. That's okay.
Cause that's what.
Never
always
too late to
drop
drop.
Oh, and circuit for that, do y'all use jumper cables like these?
Yeah.
Okay, cool.
So he
Y'all
didn't.
didn't like make your own wires?
How do you make your own wire? No, we didn't do that.
What's nice about that is that you can make your graduate very big. It's like you see on the screen, it looks really dirty. It's really messy. If you're interested in doing that, going an extra mile, let me know and I can put it in the request order to get that.
Critics.
I mean, it would be cool to know how to do it.
I can show you.
Six.
Oh, and then also, one
Design,
last thing
senior design.
before we test this, I will host office hours, for both like lab stuff and, homework related questions. I'll do my best to walk through this. This is my first time hosting office hours. I'm also an undergraduate. Like y'all's age, like, I'm not old, don't call me old. I'm not old yet,
So
How old
old.
is he?
Senior. You're graduating, right?
Yeah,
Is he a 21-year-old senior?
You're graduating this year?
Are you 21 or 22?
Nice.
22.
Okay, thank God.
I don't know what you said, I don't wanna hear it though. Okay, I got everything wired up. Let's see, moment of truth. Is this a working op amp or not? I'm gonna press this,
I don't see a
and
way.
I'm going to unscale it, that's not a pain button.
What grad?
Oh, that's unfortunate. Okay, this is not a working op amp.
Wait, you got a wave though.
Yeah, I got this, I got a really
I
noisy
am
one.
21 right now. I'm so
Boo.
But unfortunately, my op amp does not work.
Martina's like 17.
Well, I'm sorry, I wasn't all the time, it's all my is burned. I finished my burn class.
Throw it away.
I will throw it, I will
Same
throw it
thing,
away.
graduate.
I'm sorry, I brought all this equipment, for nothing, so. Components that we don't like, I'm gonna, usually what I do is if he has, burnt, I bend the pins,
An age and
so
high school.
I bend the pins like this. I put it in my pocket, I put it in my graveyard, that's what I do. Okay, I'm gonna turn off my camera now, and contacting, so. My email is my name, I can put that on a Canvas announcement. I'll email me, if y'all, for some reason, find Instagram, DM me, I'll be like, oh,
We're gonna find your Instagram.
You should track down our other.
But I should be pretty responsive, and if lab, okay, so I think lab comes maybe sometime on Wednesday, I'm gonna send out the letters of that, if y'all cannot meet during lab time, just tell me that, and we can work something together.
Is it lab on Monday?
Yeah, lab's next Monday.
Oh, sorry, office hours, times.
Oh.
And it's also, a meeting. So, if y'all know the lab, Junkins, it's like a lab, a multimedia assistant lab right across from there. I'm using theirs sometimes, that's like my own lab. I'll like knock on my door and say hi, because it's just me in there. I like company, it's pretty cool. But yeah, I think I'm prepared for anything today. If there's anything I missed, I'll send an announcement. So I did good as why.
Are you gonna teach us on
I'm
Thursday?
not gonna teach y'all.
Let's go.
Yeah, y'all get ready.
So no class Thursday? No sleeping.
No class.
That's great.
Oh, we have.
I can sleep in. No. No, I didn't.